So let us start with improper integral, and we will deal with case 1. Case 1 is the case of bounded functions on unbounded intervals. Namely, this so the function can be like this. The interval is unbounded, and so the area we aim at computing is this one. And so remember the example that we gave in the last lecture. So the definition to be used here is the following: let, this is a, here we go to plus infinity, let f function in the interval, unbounded interval a plus infinity to r. This is, suppose that it is integrable in AC for every c larger than a. For instance, if f is continuous, then you are done. Let us define the integral function capital F of c, which is the integral from a to c of f. Then we have these possibilities. First, if the limit for c going to plus infinity of capital F of c exists and is finite, then f is said to be integrable in the improper sense, in the interval a plus infinity, and one uses the notation a, so the integral between a and plus infinity of f equals the limit for c going to plus infinity of capital F of c, which is the limit for c to plus infinity, a c f of x dx. Okay? And this is the idea of a finite area of an unbounded region, so finite amount of painting in order to paint the wall, the unbounded wall. Second, if on the other hand the limit for c going to plus infinity of capital F of c is equal to plus infinity, one says that the improper integral of f between a and plus infinity positively diverges And one writes like that. This f of x dx is equal again to the limit for c goes to plus infinity of f of c, and this is plus infinity. Of course, it may be that here you find minus infinity. Then one says that the improper integral of f between a and plus infinity negatively diverges. And here the definition remains the same, but here you have minus infinity. Okay, and the third option, then if the limit for c going to plus infinity of f of x does not exist, then one says that the improper integral is indeterminate. So as an example, in the last lecture we had an example of a convergent improper integral and 1 over x squared between 1 and plus infinity, divergent improper integral 1 of x between 1 and plus infinity. And now let me give you an example of indeterminate improper integral. Do you remember the non-existence of limit has always to do with oscillations? So here we have f from 0 to plus infinity to r, and x is associated to sine of x, then sine x dx is equal to minus cosine of x between 0 and c. This is equal to minus cosine of c plus 1, and this has no limit. As c goes to plus infinity. Okay, so one says that this improper integral is indeterminate. And so what does it mean? It means that if you consider the graph of the sine, this is the graph of the sine, here you have 0, pi over 2, here you have pi, 3 pi over 2, and this 2 pi, and so on and so on. So you see the area does not converge to any precise value. You see, because for instance, if you stop painting here, remember that for definition of integrals, science is important, so there is also negative painting. So if you get up to here, you have a positive area, which is this, but then here the positive area here is completely cancelled by the other one. But here you start with positive area up to here, and so on and so on and so on. So there is no limit. Okay? Now from this definition, where there are basically three options, and this example, you can argue immediately this very important message. The very important message is the following, that before, or rather than computing, explicitly computing an improper integral, one starts from establishing what is the character of the integral. Namely, whether it is convergent, divergent, or indeterminate. In particular, let me stress that in many exercises, you will be not required to compute the integral. But in many exercises, you will be not required to compute the integral, but to establish the character, but to study its character. Stop. And this is much easier. So sometimes you're required to establish whether an improper integral is convergent, divergent, or indeterminate, and then you start computing it. Sometimes it is very difficult, sometimes it is impossible. There are much easier ways to establish the character, and very fast in general. So the next part of the lecture will be on this problem, so on the problem of establishing the character. So there are basically two scales of problems. The first is establishing the character of the integral. The second compute the integral. In this lecture, we will mainly deal with problem 1, which is new. The second is old. The second, we have to compute an integral, then to take a limit. But in this lectures, we will mainly deal with problem 1. And an important simplification, and we will see immediately why, is obtained by considering non-negative functions. This will be the topics of the next